Lean 4. So I'm working on a video for Summer Math Exposition, and the video is going to be about proving algorithm in Lean. Maybe doing some little animations about that. So I'm proving just a very simple prime sieve, which I've already implemented. It took me like hours to implement a prime sieve. It's kind of a weird thing. Let me switch over to my here. Maybe I'll make this a little bigger. Control plus. Delay there. Well, hopefully that's readable. And I'll do the little. So basically, what I've got so far is I've got a I call it a tree sieve. Not necessarily for primes, but audio stream. Right? Audio stream is not coming in. Can't do anything about it. So sorry. Basically, so what I've got here is I've got a prime sieve, and the way that works is see that it's using a bunch of arithmetic sequences. So starting with the numbers 2 plus n, so just every natural number greater than 2, and it's partitioning that at every step. So we see the first one of these things is a 2, so that's like the number that hasn't been marked off yet. So our initial state, we're going to mark that as a prime and add it to the list of primes, and then not only do we add it to the list of primes, but we track a primorial, which is the product of the first n primes. Start out with 1, we get to 2. When the list is empty, it's 1. We add a prime 2, so now we have the primorial 2. And then the next prime is 3, because crossed out all the even numbers, leaving us with the arithmetic sequence 3 plus 2n. And then what we're going to do is we're going to mark off the 3, and so then we need to break that into 3 chunks. So it's I guess 3 plus 6n, 5 plus 6n, and 7 plus 6n, and then 3 and 6 are co-primes, so we scratch those off. Hi, visiting, so hello, welcome. And so now we have so we scratch out the 3, and that leaves us the sequence that starts with 5 and then 7. So then we want to get out we want to scratch off all the multiples of 5. Use that. So we make 5 copies of both of these. So we have now 10 of these things. And we're going to scratch off 2 of them, because in each one of them will be a list that has the multiples of 5 in that. I don't really have a good, at some point I'm going to have an animation for this. Anyway, it keeps doing this. This is an incredibly inefficient algorithm here. Normally, a prime sieve, you just generate like you generate a chunk of numbers, and then you go through and you scratch them off. Like basically, you generate a chunk of like an array of bits, and you go through and scratch them off by marking them, true or false or whatever. And then the positions indicate the the ones that you want to keep. So it's called the sieve of Eratosthenes, 10 zillion years now. And then there are other primes. So this one, as I say, is inefficient, because what it's doing is it's generating these list of arithmetic sequences at every step. And I want to do a cool animation where I don't have a visualization of it handy, but you would have the line. Maybe I can draw it real quick. So you have the line. I'm getting into pen mode on this. So you have you start with the line that is just the numbers, so that the initial thing that I was doing here, and then it's not a polynomial like this. It's not a line. It's an arithmetic sequence. So you've got this. Instead of this line, you're going to have like this number, and then this number, and this number, and then this is I wasn't intending to draw anything here. Anyway, the animation is gonna be something like this. So it's gonna show this line, and then the dots on it, all the even ones will go up to a new polynomial, which is, um, instead of 2 plus n, so n is the slope, so the slope is 1. Whereas here it's going to be um, a 2n, so that you got the evens and the odds, and so that you multiply both of these by 2, and then they'll be separated. So the slope will be more like this now. It'll be twice as steep, and then all the 0, so it stays where it is. Then the 1 goes up to 2, but then we add 1 because it's right. So basically, it's going to partition these things into. So you're going to see the line splitting, and you're going to see the numbers splitting off into two different lines, and then more and more lines. And as we see that, some of these are going to be the multiples of 2, so we scratch those all off and so on. So it'll be a cool little animation like that. And that's kind of what's happening. And so at each step, you're getting more and more lines that are all more parallel. They're all parallel, and they're all more and more like leaning upward as the slope increases, and the slope is increasing dramatically because you multiply it by a prime each time, and that partitions the arithmetic sequences. That's kind of what's happening. Like I said, I'm going to make a video this summer, and so that's going to be all nicely animated, and that's kind of the idea of it. Anyway, so this thing exists. Kind of where I'm at so far, just to tell the story, is I implemented this thing. So I implemented arithmetic sequences. That has its own little theory. I didn't prove anything about them yet. I just wrote them. So Lean is both a theorem prover and a programming language. And so I just wrote the thing. So it's a 2-term binomial with constant term, or with integer terms, or I guess natural number terms. So you've got the constant, and then you've got the difference. So it's always going to be k plus d times n, where n is the input number, the input sequence. And then I came up with some arbitrary way to order them because I want to sort that list. Winds up getting it gets all jumbled together because the order is just based on which one got multiplied, and they're just next to each other. But they're like twin primes in here next to each other, or basically these should be ordered, right? So the first one should always be the one that's the smallest next possible prime, and that's not the case right now. So that's what I'm going to work on at some point. But in any case, it already does. It already scans through the list, it finds the smallest one, and it generates the next prime. Figures out the smallest coefficient and gets the next prime. So since the difference term, the difference coefficient is always the same, then you just have to look at the smallest one to find the next possible prime. It's always going to be first one in one of the sequences. But I haven't proved that. Like, I know that's true. I know that this works. I can see it generates primes correctly. And then so the idea was to actually generate to actually create a proof of that. So the very first thing I did for that was I made these. You can see, like, here's, you can evaluate terms. So here's these are the first 10 terms of just the identity sequence. Here's the evens, here are the odds, and so on. And you make them by just saying mk, and then give me the 2 coefficients. And then there's a pretty printer. Okay, and then pretty printer is doing this, right? Showing I write it kind of backwards because this is how I think of it. It's like this: the first entry is the x to the 0 power, the ones term, and then x to or n to the first power, and then if there were more in a polynomial, there would be n squared would be the next term. So in rising order, kind of backwards from how you do it in math, but how J does it, how the programming languages I use tend to. Anyway, so the idea is that in this sieve is that you have these arithmetic sequence. Oh, and then and you can also compose them so that give it one sequence, you can give it an input sequence, and it maps every value in the input sequence to the output sequence, and creates, and tells you what the numbers are. So it applies Rn is S of Tn or whatever. And then somebody showed me yesterday, Mario Carniero, who was one of the maintainers of Lean, or at least works on Lean quite a bit, been around in that community forever. He showed me you could do this, which is basically just use the sequence that you made and just apply it. So here, the function is called terms, and then you can see that the signature is popped up. So it takes a sequence called S and a natural number called N, and it returns a list of natural numbers. Whereas here, the sequence itself is taking the parameter. So here, these two arguments are being passed to terms, and here, this one is evens is taking a term. So it's acting like a function. All right, so that's pretty neat. But I guess the main thing I wanted to show is that you could compose them. That's what does the partitioning. There actually is a so partition here says partitioned it into n slots or n different sequences. So we just loop through the range n, so 0 up to that number, and we just feed it in, n times, n was a bad word, but n is the coefficient here, so n times the input n plus I, where I is one of these numbers. So if we start with IDs and we pass in the number 2 here, we would get 0 plus 2n and 1 plus 2n, and that would be the even. All right, so anyway, then so I did that, and then from there I made a prime sieve. My idea for this, I call this library tree sieve because it's actually meant to be used for any kind of work, not necessarily for primes. In fact, that wasn't the, I was actually going to do last year. I was going to do a video on the Collatz conjecture, and specifically about trying, like, how do they verify when they run all these programs people out there are running programs that trace the path of a number through the Collatz conjecture, which is that thing that says, if a number is even, then it divided by 2, and if it's odd, you 3x plus 1, and you just keep iterating that, and numbers go up and down, and eventually basically every positive number anyone has ever looked at, it goes back to cycle 421, 421, and Collatz conjecture is that all numbers do that. Knows how to do any work on it. So people are verifying, and they verified it up to these huge numbers. And my video was about how you could use this kind of thing to programmatically describe equivalence classes. So again, you're talking about evens and odds and doing different things for evens and odds. Well, it's not just that. In the Collatz conjecture, you have like numbers that are even, and then they land on another even because they're they're power of 2 or they have power of 2 as a factor. Anyway, the point is that the verification algorithm would use a structure like this. But anyway, somebody was talking to me about primes, and so I made a prime sieve, and that's what into this. So anyway, so the goal is to prove it. And so what I have so far is the idea that I came up with this. This was the first thing I proved in quite some time in Lean. I'd done this. I'd messed with Lean like 2 years ago, and my first attempt since then. Prove something, and it's not terribly pretty, but basically it's the idea that if you are if you have a candidate prime, I think you have the number C is a candidate prime in the natural numbers, and then we know that these are hypotheses. Basically, these are arguments, but in Lean, like a hypothesis, a proposition is a type, and so this is an argument of this type. The type is 2 is less than or equal to C, and it's referring to this C right here. So you actually, called a dependent type system, and you can write very elaborate types that take that that depend on this variable that you're passing. So they depend on each other's on other parameters, and you can build up these. things. They depend on values, named values. And so this is another hypothesis. H is for hypothesis, and this is no prime factors. And it says for all p less than c, if that p is a prime, then p does not divide c. So that's kind of the fact that we know about. Like that's kind of like what a prime sieve is tracking. Like we're tracking somehow like the list of sequences, or you know, whatever algorithm you use to generate your list of numbers that are not crossed out yet. They all, you know, the numbers in that set are the ones that have this property. They have no prime factors that you are aware of. No prime factors less than the current prime. Hey Batlin, I was just glancing at the Lean tutorial a few weeks ago, and it seems kind of neat. I'm guessing it fits in the same sort of space as Idris. Yeah, I believe they. I haven't worked with Idris that much, but I believe they both have a dependent type system. They look a lot like Haskell. This one just happens to be geared really towards proof. F star I've not seen. Agda is another one. There's another theorem prover called with the unfortunate name Coq, COQ, and it's similar to that, but I haven't used any of those. I've used Isabel, which is another theorem prover, and I guess the main difference is Isabel is like you have whatever logic you want. You write the logic in ML, in a meta language, and then you build up whatever you want on top of that. So there's different versions of Isabel depending on what kind of logic you want. Whereas this one uses dependent type theory as the logic. And so you know, when you write stuff, when you want to extend the proof check or whatever, you can write it in Lean, because everything in Lean is there's no meta language. It is its own. There is, I mean, it's part of it's written in C, but it's written in. Yeah, they were going to change the name, and I saw that on Twitter, but maybe that was an April Fool's. Never happened. Anyway, so what I proved so far, no prime factors implies no factors. So no factors at all, because this is the fact that yeah. So this is a fact in the library, and you see when that pops up. I don't think I put my. Okay, I can. It says not prime p is equivalent to the conjecture that p is greater than 2. So and so p is a natural. P is greater than 2, and for all natural numbers less than p, if m divides p, then m equals 1. M is equal to 1. It's kind of a weird definition, right? I think of it as not having any prime factors, and this just says no number smaller than it divides it unless it's 1. So that's what I had to prove. So I couldn't find anything that has this condition in the MathLib library, so I had to, you know, I had to prove this statement. So I had to arrive at this statement from these statements and that. And I guess the proof says, and one thing I did like about Isabel is it has a really nice, like, readable proof system. This is not quite as readable, but it's not just like lists of tactics and stuff. So you actually, I can kind of read this. So in order to prove this, we're going to say, or we're going to derive that statement that for all m at all for every natural number less than c, m divided c implies that m equals 1, so m is the only one that divides c. And we introduce some conjectures for that. So we introduce the actual letter m, and when we put our cursor here, you can see m, HMC, so hypothesis MC, so m is less than c, HMDC. You can see it broke it up into 3 pieces. So these 3 pieces. And then from that, we have to prove this part, that m is equal to 1. So how do I do that? Well, I'm going to do it by contradiction, by saying, assume m is not equal to 1. And when we do that, it introduces this kind of like anonymous statement that not m equals 1. So then we're going to obtain. So basically, we're going to take this statement right here. So taking this statement, I'm just stating that, and then the proof of that is this. So the statement is there exists a p such that p is prime and p divides m, because P is not M, and so like, sorry, P is not prime. So if a number, sorry, M is not prime. If a number is not prime, there must have a prime divisor. Sorry, if a number is not 1, then it either is a prime or it has a prime divisor. So there exists some prime that divides M, and so that's this theorem right here. And it needs the fact that M is not equal to 1 because M1 is not divisible by any prime, right? So anyway, so we get that, and then so I made up this statement in order to obtain this letter P, and then these hypotheses that P is prime, so HPPP. You can always see it over here. P is HPP, H is prime, and then HPM is P divides M. Okay. So those are the hypotheses. And then from just this fact, we can just we can use the transitive property of division to show that P divides C. Okay, because we said M divides C, and then M is not 1, so then P must divide C. And then we have to show the opposite, which is that basically I needed to say, well, I need to say this statement, and I just went through some steps to divide this statement, and some of these are little facts that maybe you could, like, I wonder if you can just say it like this. No, sometimes you can fill it in with like if you put an underscore there, you can just fill it in automatically. But this is not. I wonder if you can say rel here. No. Yeah, so I'm still fumbling with this. So Linnereth is a tactic. So I guess I should say what it's doing. I'm part of this. I'm like rehearsing my own like way of explaining things. I'm not an expert in these, but as I said, the type system can express very complicated things. As with any language, you can give your variables a type, but like this right here is a type. So PLTC, this is a type. The type is a proposition is like a kind of type. So there's like a higher order type system. Like a proposition is a kind of type that doesn't really contain a value. It just either is true or false, right? But this is the type. Type is that given these two variables, C, which is a nat prime, and P, which is a nat prime, that the value of that P is less than C. Okay, so this is a prime less than some other prime. And it's a proposition, so it's being applied to, so it's a type, right? So so this is the type or the set of all primes that are less than C, right? So primes less than C it is a type signature, and so you can if you have a value of that type, you are asserting if you have a value of that type, you have proven, given your assumptions, that there is a value called P that is a prime and it is less than C. So you had to construct this thing, if that makes any sense at all. And this type right here is like an empty value. It's like a phantom value that it has no data associated with it except the type itself, which is the statement, right? And you can treat it like that. So now when you make a proof, all you're doing is you have a bunch of these little phantom values that I call them phantom data because they're in Rust and Haskell. There's a type called phantom data that just associates a type with nothing in RAM. It's just a pure type signature, and that's kind of what these are. So prop is like that. It's completely happens at compile time or proof checking time or whatever. But these values gets passed around, and you can pass in the assertion like if you have something like this where it says M divides C, this looks like a function, but it's also like an implication. So in logic, this is an implication, and in functional programming, this is a function application. So if you have a value of this, this proposition, if you have a value of this type, this prop, that M divides C, you can pass it in as the first argument to this expression, to this implication or function, however you want to look at it, and you'll get back a the assertion that m is equal to 1, provided you also have this one. Right? So if you have these two, m is less than c and m divides c, you'll get back to this thing when you pass it to this rule. When you pass those two facts into this rule, it's like passing function arguments in. And then this would be like the implementation of that, except this is just this happens at compile time too, and it's just a proof, right? There's no actual computation being done at runtime. There's no actual function being called. It's just using the mechanism of a type system and function application, and then the type checker for that to implement a proof. And so it's called the Curry-Howard isomorphism. And Curry and Howard proved that, I don't know who Howard was, but Haskell Curry and whoever Howard was together, they proved that there's an isomorphism between functional application and proving in this like in logic. I'm not an expert on this, right? So hopefully I'll be able to clean up that pitch before the end of summer. Anyway, I finished this. I managed to do this. I was happy that I proved this one fact, because I figured that this is the information I have in my prime sieve. This is the information I need to tell Lean that something is prime given this information. And so now I can say, well, okay, if this number, if I can demonstrate that my prime sieve is working with these two facts, then I can show that it's generating a prime number. It's easier said than done, but the idea is that I can. The hope is that by showing that I've somehow tracking the fact that I've removed. Let me say this again. All right, so I'm trying to prove that a prime sieve works. The prime sieve is based on this notion of partitioning arithmetic sequences, and not only partitioning but like scratching out arithmetic sequences. So at any given step, there'll be so it's again, so a sequence looks like this, right? Kn plus d. Right. So if k is of the form like say the number we're looking at is like c is the number we're looking at. Say p is the prime, right? We're looking at. So if it's p times j or whatever, so k equals p times j, and then d is the primorial. So k is p d is going to be the way this prime sieve works is that d is 2 times 3 times 4 times 5 times, or let's write it this way: 2, 3, 4, 2, 3, 5, 7, 11, 13, so on, all the way up to whatever p is, whatever that prime is. So that means that d is equal to call it some other thing, the previous primorial, times the current prime. So we have something. So instead of k plus dn, we have pj plus pqn, right? And so this factors out to pj plus qn, and then that means that every number in that sequence is going to be a multiple of the current prime. And so we mark out anything where k is of the form is a multiple of the multiple of the current prime that we just found. And then that's how we do the scratching off. And there could be many of these. There could be several sequences. In fact, every time that we split one, we're going to wind up with one that looks like of this form. So if we're splitting into 5 pieces, I don't know. Say we had 10 to begin with, and we split them each into 5 pieces. We're going to have first we're going to have 50 sequences now, but then we're going to mark off 5 of them. Or sorry, we're going to mark off 10 of them because there was one for each of the original 10. That winds up being this form. So that's that. Because what we're doing is, we're taking the sequence and just dividing it into 5 pieces for the number 5, however many, whatever the prime is. So what I want to prove is that by doing this, that is somehow, well, I mean, it is tracking the what it leaves after I scratch all those off is this set here, the set of of the set of natural numbers. Oh, I shouldn't have called it a C. Okay, but it's a set of natural numbers that are left over, right? That are left over because they're not divisible by any of the primes. That's what we have, and I need to prove that. So where I started with this was I wanted to, I wanted to prove that directly about this particular algorithm, but I also want to change this algorithm in the future and like show that, like I want to maintain the proof that it's still working at every step. And so I was I was thinking that it might be nice to write it like an interface in Java or something, where the proof is like some kind of type or class or something that that is somehow associated with the algorithm. And if the algorithm can produce something of that type at every step, then I can make a proof about the type and not worry about the algorithm. Just prove that it's producing one of those items. I don't know if that makes any sense, but like what I'm saying is like a prime sieve here. So this is so in the main routine, I've actually got the step function where I do all the calculations for what I do from step to step. But then completely independent of this, I've got this right now, which I say is class prime sieve, and it uses these functions to define, as again some types that are, the natural is less than a given C. So given C, the type of all natural numbers less than C, given C, which is a prime, the type of all the primes less than C. And then so we can use type checking to show that something is or is not a member of that set. And then here, this is the condition of all the things that are not crossed out yet. So coprime to the known prime. So coprime means it like it might be the number, like 15 has 3 and 5 as factors. It's not a multiple of 2, so it's coprime to 2, even though it's not prime. It's coprime to a particular prime. And so if it's coprime, which is to say none of the primes in question divide it, then these are the ones that are not scratched off yet. Right. And also we want to get rid of 1 and 0, so we say greater than or equal to 2. Okay, so then given these definitions, we say, well, we have that are prime sieve, and I'm probably you can see I renamed the file to prime gen. I'm probably going to call this a prime gen. It doesn't necessarily have to be a sieve, but it seems like that no matter what implementation you want to be able to refer to that set. And so I made the set, and this is like a default implementation. So this says that any prime set, so class is like a like interface in Java or something, like class in Haskell, interface in Java or whatever. So it's a generic thing that, or a trait in Rust or whatever. And so it's a thing that any structure can implement. And so this is the default implementation, that it just is it is this type, right? It is the set of prime, n prime is just nat.prime is just a natural that is also prime. And so that type just is the set, right? So you can assign that type to the set, and it's just like a type and a set are very, not exactly interchangeable, but they're very similar concepts. It's like the set of all this, like a filtered version of that type, right? So every member of that type that implements a that satisfies the proposition. But this could be overridden by a it could be overridden by an actual implementation of this class. So, so this is not a very good way to model this in Lean. So basically, these are like the this is like an interface, and it has like some what do we call them, default implementations. So the default implementation, so basically every prime sieve will have an S, and it will have this HS hypothesis, which is a proof that is a proof about S, right? So S is some set of primes, and by default, the implementation is this, so you don't have to specify that yourself. And then, like, in order to make sure that you don't change this, you have to have this, which is to say that for every value in that set S, this condition applies. And so, obviously, this implementation works. So I still don't even know how to use this, but so we could prove this, right? This ought to be simple to prove. So okay, so ChatGPT or Copilot is giving me this simp PTLC intros assumption. No, that did not work. I almost never does the LLMs actually prove anything, but they sometimes give you a good idea. So this actually worked up to this thing. So we can look at this, right? So we want to prove this statement given S, and this is like the default proof, right? So if you change this, you have to override this proof as well. And I'm not going to do this. I'm not going to keep this around, but just for the sake of argument, let's just show what this is. So I want to prove this statement given this information right here, right? So this is all we need. We need to know what CX is. So C is this prime. And we need to know what PLTC is, which is this, that P-val is less than C-val. And because like this, because we're like, this should be trivial, right? Because we're saying here's the set, and it's all these values, and then we're saying for every value in that set, this applies. So this should be absolutely trivial. Prove. So what do we have? So when we first start out, if we write the word sorry here, comes out a little cleaner, I think. So these are all the facts that it knows about, and this is the thing we have to prove. So it says one goal, and we have to prove that for all P and S, we have to prove that statement that we just said. And sorry proves it. All right, so what does this do? If we move the cursor up and down, you can see that it changes this. So it changes that P less than CX, it changes it. So it's basically taking PLTC and applying it. So it's simplifying it based on the definition of this. So it's using this to replace PLTC here with this expression, and you can see that as I move the cursor up and down, this little red part changes. So if I go, see, changes from PLTC. This is the red is what's being removed, and the green is what's being added. So P is less than CX. Okay? And so now what do we have? We have, for all of these, we have to introduce, we have to produce a value of SX. So we want to introduce something called P probably. And after I go down, yeah, so you see it gives you kind of redundant information sometimes. So I didn't give it an explicit name, so it introduced something called P. You can see that I didn't explicitly name it, so that's I think I don't know what this dagger symbol is for. Seems to be that's a auto-generated name, and then it gave me a hypothesis A that P is like this. So these are facts now that we can use. That P is a member of SX, and we still want to prove that P is a member of CX. So maybe we can't prove this. Maybe we can't prove this at this point because I don't have any facts about S, right? Or do I? All I know about S is that it's an N prime. I don't have this fact that I assigned it to PLTC, right? So maybe you cannot make a proof like this based on this default implementation. You could only do it based on the type here. So I don't know. I don't know that I can prove. I don't know that I can make any further progress in this. Can I define, can I simp based on S? No, I didn't do anything. But we would have to say at A, right? So let's call this P and HP at HP, right? And that doesn't work, right? Yeah, that doesn't do anything. It doesn't give me a res quickly. So yeah, this is what it's going to be like. This is how proving is for me right now. I'm not skilled enough to do this well, and I'm still struggling with like every little step. So I don't have a lot of practice with it. But I don't think I can prove this because look, we have to prove this, and there's no fact unless we can somehow refer to this default implementation here. And I don't see anything, like I don't see the fact that I've defined this in my list of assumptions. So I don't know that you can do this. There's nothing in the documentation to suggest you can do this. That you can make a proof about a class while it's about these implementations, right? All we know that is that the only thing the type knows is that it's a set of n primes. It's a set of primes. So sorry, yeah, a set of primes. That's all we know about it, and it doesn't say anything whatsoever about this. And I don't think we can prove that for a class. I think we can only prove it for a structure. Or we can change that to structure to see if this works. Ah, okay. So now I mean, I think we would write it like this. So you write it like that, maybe like this. Can we not do that? I think you can say this, but I don't know how to do it right yet. I'm getting off track too because I didn't really. I don't need to prove this, right? I'm throwing this away. So let's just ignore this and prove and move on to something else because I'm gonna fumble at that too. But at least I'll be making progress towards my actual goal. So yeah, my assumption, like I kind of made up this style, like thinking this might be an interesting thing to do. And I had a long conversation yesterday on the Lean Zulip chat yesterday, and Mario Arniero was very helpful. And so I'm going to take some of his ideas that he did. So he rewrote this for me. So he had this. So he basically took what I did and rewrote it like this. So he called this a class. I'm going to follow his steps. So prime sieve, he called it base, prime sieve base. And we say open prime sieve base, and that just makes these things available. Okay. Just to refresh my own memory what he did. So rather than having this attached to the class, he defined it using like a function that is gonna be one of these. It's gonna take one of these, and then from that we're gonna get. We pass in the argument it. You see it says prime sieve base a. So this is like an anonymous parameter to this definition. Just the fact that alpha is a subclass of prime sieve base, or is is an instance of prime sieve base type that is an instance. So this is a type. Then we say we have x as some value of that type. And then from that, we're going to produce an n prime. And that's because this type has sieve, which takes an instance of the type and produces prime, so it produces a specific prime. So from that we can generate this. So this is exactly like a method, except it's just detached, right? So it's an associated method, but it's not attached to the class itself. So let's just take this. So let's see. Why didn't this work? What happened here? Sieve base a alpha set n prime equals p. Invalid field notation less than. Why did that work? How? Maybe he didn't do this in Lean. Maybe he just did it. Like he was just doing it in the editor itself in the chat. That doesn't type check. Let's see what happens. Oh, wait, did it go away? Where'd my error go? Yeah, sometimes Lean does this. Like I think these lines, they're added lines. So, I mean, but sometimes you see lines over here that indicate, these lines. Okay, so these lines are saying it hasn't been processed yet. I guess it's taking its time. Maybe Lean has crashed. Oh. Sometimes this just happens. Oh, you see those? It just takes a while. Those bars went away. Okay, so now I don't get an error here. So happy with that. I don't know why. It took a minute to prove it. I don't know why it sometimes shows like an error here. Like, or in different places you'll see like an error pop up and then it goes away. Maybe that's just like a bug, and I don't know. Okay, so basically the same thing. He defined this SNR instead of being on the type themselves, and that way you don't need a separate hypothesis for these. I think what he's going to do in a minute, if I recall from yesterday, is now he defines prime sieve, and he has all the I didn't mention them, but all these proofs. So my thought is that you need to prove these things about your implementation, and these are like helpers that are provided for you. So now he's moved these into external definitions. So he broke it into 3 pieces, or 2 pieces plus these 2 definitions. So let's say class prime sieve is what he said. I'm trying to do it like from memory. So it is alpha is of type U. U is universe, so it's I guess parameterized on some universe. Extends prime sieve base. Yes, did he do that? Yep. Where? So this is a sub class of this. And now he rewrote each of these. So let's see if he can. I think these would say the same because they were functions before, and they are type checking. Okay, so they didn't require any changes. Yeah. So what do these say? They say exactly what the comments say. C is in R. So given a value of this type, we want to these hypotheses take a value of this type and prove that that these are true. So there's no proof here, right? These are things that you have to prove. These are fields that are abstract fields in this class that your implementation of this class has to implement in order for it to be a valid member, to be a valid implementation of this class. So my thought was that you would make these requirements, because if So you have a set of primes S, the known primes, and then the remaining numbers, which is all the integers that are not multiples of those primes. What it says, n is greater than 2, and for all p in S of the same uh, base, right? The state, right? This is the state. I'm going to call this prime gen state. To prime gen state. So for each one of those, or maybe prime sieve state, because this is kind of like talking about what a sieve does. Prime sieve state. So given this state value, we have to prove all these things. And really, it could just be what am I trying to say? This could be like the. I was thinking like rather than using inheritance here, I could use composition. So we would say that X is a instead of extending it. I don't know how to express the idea that maybe we could say X is a and maybe instead of type we would say prime sieve state. Or maybe we just say this, X prime sieve state X. Wait, hang on. We need the alpha because we're parameterizing on some type that you define. Alpha is the type you define, but then we can say you have a prime sieve state based on this, and then now we can get rid of this parameter everywhere. I would think. Right? Oh no. Why not? Why can't you say that? Delta synthesize prime sieve state A. Oh. Well, I mean, you can do this. We need to say like I don't know how you would say extends. Maybe A is a subclass or A, not AL. You can do a lot of Unicode characters, but like \A and space, then you get alpha. A extends, is that a keyword? Extends. Maybe we just say prime sieve state A. I don't know how to express this idea on A as an alpha. Oh, that worked. Okay. Okay, so that yeah. So the brackets mean what this says instance implicit binder. Basically, you don't have to specify this. You just have it's just somewhere in the scope. There has to be an instance of prime sieve state of your type. Then you can implement this, which is your proof. Call this prime sieve proof. But I can already see that down here something is going wrong. I think Oh, because we changed the thing. So yeah, so this is talking about that previous thing that we now cut up into little pieces. This is not going to work anymore. Why doesn't this like that though? Well, since so you have to say prime sieve state alpha and prime sieve proof alpha. Okay, and then all this should. Then we want prime sieve proof. Get these. Well, it doesn't matter. This is trash anyway. Like I said, a lot of this. All right, so I didn't have to do that. Maybe that's not necessary. He's going to get rid of this as well. Kind of just doing exercise. All right, so then he says, okay, here's an alternate structuring. Eliminates the type alpha entirely and just uses an abstract state. So we just have C as a nat. We're going to have a structure for the state, but in this formulation, there's only one number in the state. The current prime value is C, so it's over. The idea is in practice, you would prove that your prime sieve relates to some abstract state C, satisfying prime sieve, okay, and next returns a value which is related via prime sieve. Okay, so this is kind of what I just did. Probably gave me the idea yesterday. I just haven't consciously in my head. So prime sieve, okay, the prop. That threw me for a loop yesterday. So structure can be a proposition. Prime sieve, we call it spec. Gets rid of that type. I wonder, maybe what we do is we say curly braces here, and then make this explicit. So you have to have the spec for your type. Right? Did not like that. Failed to synthesize alpha is a prime sieve. I understood. My understanding was that would not make any difference. Okay, I don't know why that makes. All right. Anyway, I don't know why the brackets make a difference. This binder. Yeah. Oh, so it controls whether the if underscore is used. Okay. Instance implicit binder like the instance implicit binder inserted and solved by type class inference for the specified class C. So this is something I'm not ready to process this. This is not a. I said this is me being a newbie here. A lot to take in. All right, so square brackets work. I don't. And then these, what does that do? Implicit binder If all parameters before have been specified, then a so you just don't have to pass this in. Okay, so going back to Mario's questions here. So he made a structure. So here, this is not a spec, this is a structure. And from that, he said he was able to, well, no, he lost that type because he reduced the state to just C. But I think you need init and you need next, because yeah. So like he says, I was going to have a structure, but in his implementation here, he doesn't have an actual algorithm, right? He's just, this is all abstract, and so he cut away too much for clarity, right? He cut it away for clarity, but you know, I have to add it back in because I can't just track a prime number somewhere. I have to, you know, the algorithm has to do something. So you have to be able to say init, you have to say next, and so that's a step, and then you should be able to watch this change from step to step. Okay, and at every step, these are the conditions that should be true. But I think some of these are redundant, and he proves this. Then he says next. Okay, so he says he breaks this into 3 different. I don't know why he broke this into 2 structures, except that these take a because they have the before and after. All right, so let's see what he's doing here. So this is like a constructor syntax. So given a structure, these are the arguments to that structure. So C and C prime. No, sorry. This is a proof. So in order to fill in, so prime sieve next takes C that is n prime. And C is a natural number, and here we need it to be a right. So this C is a natural number in prime sieve okay. Prime sieve next, C is a prime, and so to prove that this, so we have prime sieve okay C, so it's a nat. Now we want to prove that it's also a prime, and so we have HC, the hypothesis that the prime sieve is okay. Then we can prove that nat prime is a, or that the C here is a prime, and this is the proof of that. So in order in order to do the typecasting right, we have to provide the proof that it's actually this type. N prime is actually, as I defined it, it's a type, and it is a subtype of nat. Does it say subtype? Yeah, so it's a subtype. It's a subtype of nat where that natural number is prime. So it's a natural number that is prime. And so, you know, I could define types for these, you know, these as types as well, but I wanted them to be a set. So as I'll say in a little while down here, that I want to be able to explicitly put something in that set. And I don't know if I'm going to do that or not, but that seemed reasonable to me. Anyway, so anyway, so that's the proof, and then C prime is just what? Where does C prime come from? So this is something I've learned about Lean. If you just make up a letter like this, if it's a single letter, I think the rule is if it's a single letter, then you can stick it in here and you don't have to define it anywhere. So like because a thing called C goes in that slot, like this is defining a new parameter to this thing called C, right? To the a theorem is basically like a function, right? Let's see if I put this here. I guess we have to do all this. Or let's open up the Scratchpad here. Copy all this thing into this. I don't know what to do. And then I need my definition. Doesn't know what nat prime is. Prime. Good. That doesn't know what nat prime is, so we need two of these. I'll take one of them. All right, so then this should refresh. Line should go. See, it goes through multiple passes, I think. So like one pass did the syntax highlighting and got rid of the errors, and another pass did the type checking, maybe, or the proof checking. I don't know. All right, so it uses sorry, so things about that. But so what I wanted to do was like print this somewhere. Yeah, see, so it created these parameters that are hidden based on the letter C. And I think if you call this like C, if we call it cabbage or whatever. No, okay. Maybe it's not just any letter. I think you say set option pp implicit true. Auto implicit. Yeah, then it's mad about this. So you have like implicit declarations of these things. Yeah, and you have to explicitly define them if you have this set. Which tripped me up one time because I used the word like I wanted to have a natural number somewhere. Like I said like x is nat, and you see it's squiggly marks here. Well, but without this thing, works just fine. And the problem was it was capitalized, and I said, well, capitalize that letter, and the error was like 30 lines down or something like that. Anyway, okay, so again, I'm looking at Mario's suggested refactoring here, but he says here's an alternative structuring which eliminates the type alpha entirely. Blah blah blah. We did that already, so this is what I got. Did I copy and paste the wrong one? No, this is what I got. What I just copied and pasted. At this point, though, prime sieve OK is just some predicate on natural numbers, which probably has a name already. Indeed, HC and R is provable outright because C, being prime, is coprime to all primes less than it. C in R. So you shouldn't have to prove this. So this is something that if you're in a proof, if you need this fact in a proof, you can just derive it on the spot. So we don't need, it's not that we shouldn't put the burden on the implementer who wants to prove this, that's the case. All they have, these are the things you have to prove that your prime sieve works. Okay? And the hope was that this would be simpler than like, or at least would give you like some structure to aim for with your proof or whatever. All the additional assumptions are unnecessary in prime sieve OK. It's just not named nat p, not prime c, because oh, hang on. So this was wrong. He made a mistake here, and I confused me a little bit. But okay, this guy is like a fountain of information. He just misread my definition. So this is not false because he said it contained non-prime numbers. It didn't, and he corrected himself later. And then S max is trivial true by definition. And that is because I guess over here. I mean, he's right, but I couldn't see it. So like, so here S max is like the whole set of natural is less than C is natural is less than C value, and or whatever, and so naturally C is the maximum of the set. So you don't need to prove that. Right? So, or even for values in S, like it's like for S, it's primes less than C. S is defined as primes less than C. So when he replaced this nested definition where I had, I don't have it on the screen anymore, but it used to say S was something about this. Like I wasn't seeing this exact phrase here. So this is trivially true, and we can just get rid of that. And C, oh, I think I erased it over here, didn't I? Like, so which one? So C and R is provable outright because coprime to all the primes less than it. So that is part of the definition of R. The idea was that in my mind, I was thinking about the steps that you have to take. You have to say, okay, I have R, the set of all. I have something representing the set of all the of all integers that are not scratched out, that are coprimed to the things I found, and I want to take one of those items, and so that's why I had this in here. But I'm gonna just call this trivial. So I'm gonna leave it here, trivial, but like like I want you to produce a value of that set. So maybe what I want to do is that C needs to be, yeah, maybe this needs to be like a type, right? Like rather than having this as a hypothesis, this should be the type of C or something like that. Can I do that? Can I say, so instead of this, we would say, well, okay, hang on. Oh, hang on. I want to refer to this, but maybe I can't. Did I say S is a type? Can I say, let's call this like ST, right? Because it's a type. I don't know if I can even do this. So it's an experiment. ST is a type. I don't know how to say this. I want to say, like, instead of making it a set, can I just say, oh no. Oh, I see, because like it's a circular definition. See, because yeah, I can't say what I want to say because like I want to say that C is a member of R, but R is defined in terms of C, right? R is defined in terms of S, which is also defined in terms of C. Right? CIX right here. CX. Okay, so whatever. That's not gonna work. Trivial, but keeping just trivial, but maybe useful. I don't know. All right. So anyway, so you take C out of so at the basically you got a before and after state. C is the before state, or C is the in this case C is the prime before, that you're looking at to begin with. So you start out looking at 2, you have nothing in S. Oh, well, see, yeah, and like you want to say S is given A. Can you say this? Yeah. We have to give this a name x, right? So I'll call this x. So this is a set of those values. Yeah, it's it. So given x, so given the instance of the prime sieve, we need to be able to produce this. We need to be able to produce this step. And the implementation would be what? Like we can give it a default implementation. Again, I don't even know if I need this, but is that going to work? What's wrong with that? Unknown identifier x, it's right there. Oh, okay, so we give it a parameter, and it's going to return that. This is the type, and then the value is this. Okay, so then we say set. Application type mismatch. Okay, this is like I'm doing a lot of struggling here. This is not going to be expository because I do not know what I'm doing yet. I feel like that's an implementation of this. This says right, so application type mismatch. So I have been using Copilot and whatever. So let's see if it can give me a suggestion. Usually it doesn't know what to do exactly. Oh, so just change it to that. Okay, so change it. Literally change it to change set comprehension to the subtype. If that's the case, then I'm not doing what I want to do right. Can I just return the empty set? Yes. If I put it in parens, then it's going to want me to prove that that's I think yeah, I think this is valid. I could put something in here like a 2, but I would have to prove that the 2 is less than C, but I don't know what C is yet. So the only thing that it can be is an empty state. Is an empty. If I put a 2 here, it's going to fail. If I make it empty, that's fine. Okay, so this works. This is all I can do. So in other words, like I have to, because this type depends on C, and I haven't decided what C is yet. Like C is something that the implementation provides. But I do think. Oh, that worked. Okay. Oh, I think I didn't have the val before. Yeah, I didn't have, so I needed this val. So the fix of this, okay, so this actually worked. This is what I was trying to type before. So I'm confusing myself sometimes because this looks like a set comprehension to me, but it's not. This is a subtype. So this is just a subtype of n prime, which again is a subtype of nat. N prime is a type. It is a subtype of nat for all natural numbers that are prime. Right. So n prime is just nat prime. Oh, well, nat prime is a proposition. This is a subtype of nat. So it actually is a type, whereas this is not a type. This is a, you can't say n nat prime. You have to say nat prime n. Right? It's a proposition about a type or about a value, whereas this is the type of those values. Okay, so now I'm defining a type on the fly. This is an anonymous type that is all the prime natural numbers that are less than whatever C is. C is, we're getting this state. We're getting the implementation of the prime sieve state on that X, and from there, we get C of X. Okay. I think you can say X dot C properly. No, you cannot. Not clear to me why you cannot. Oh, because you would need a prime sieve state, not an alpha. Alpha is the wrapped type. Anyway, so this is the default implementation of this, right? This, yeah. You could either assign it. Yeah, this kind of makes it. This is kind of the feeling I wanted to have. Okay, so you're going to implement this. This is like a trait, right? Or interface, right? Your implementation implements this, and these are the things you have to implement. You have to provide a function that returns a prime number, and then you have to return a set from S. But if you don't, then by default it's just all these things. However, like you have, if you do anything other than just use the default set of numbers that is there for you, that I'm defining for you here, which is all the things, you have to prove that you're explicitly doing this. So you could start out with an empty set, and then you say, I'm going to take that set and add a number to it, and then prove that that operation is maintaining this invariant, that it's still a member of this type. And so that's kind of the feeling that I expected this to have. Like, you'd have to prove that adding something to this set maintains this invariant. But if you don't supply that, then we just recalculate it for you every time. We just generate the set for you every time rather than you mutating it as you go along. The reason being that you're not going to just have this set. You're going to derive this set from the state of your prime sieve, right? You're going to say, and really, okay, well, for example, I don't track a list of primes anywhere. I don't track a set of primes anywhere. what I track, the thing that my thing is using, is that I have all these arithmetic sequences. They all have the same slope, and that slope is a primorial, and a primorial is a natural number that is a product of the first n primes. So the set of these primes are the factor of the slope, right? Are the factors of that slope. And that's the only way that my algorithm actually tracks that. So I would provide a mapping to and from I could provide a mapping to and from that primorial to show that I'm tracking this. I don't have to, because it's implicitly there, and I've defined this thing here, so I can just define it on the fly. I can just refer to the set of all, like this here just says, here's how you create the set of all these things. Here's how you construct it if you really wanted to. As C gets bigger and bigger, that would be a bigger and bigger set. You don't actually have to have this in memory. What you really need to do is just prove that you have a set of that type. I don't think you actually have to construct any kind of like physical thing in memory, as long as you can show. I don't know if that's true or not. That's not clear to me. But I wonder, okay, so I was trying to do it as a type. I wonder if rather than having to have an explicit object here, we could just have st, right? So we say s, the type of s, and it would be a set. No, hang on. It would be this. It would be the type. Okay. Do I have to provide it now? Can I just like do that? I'm not clear if this it's not clear to me if this makes an obligation or not, because it's just a type. Like it is what it is. Maybe I just put this here. I'm not sure. Okay. So I ought to be able to return a type if I wanted to. As type, but is expected to have type. So if I construct this is the universe thing. Maybe I cannot do this. I don't know. You see, it has a type 1, but it's expected to be a type. But not only that, it's supposed to be a type that is that type. Like it's supposed to be. Okay, I don't know if I can do this or not. I'm just going to leave this as it's allowed. I don't have an instance of prime sieve state, so I don't know. So let's just say structure X, structure foo. Okay. Yeah, this is not a state. See, it's trying to. Hang on. So all this says is, yeah, I can't do this. I can't do. I can't. You can't return a type. You can return a type at a like in a higher universe. I think. I don't think I can do this. I'm. What this is saying is that given what I wanted to say is that given x, return a type. Can I do that? Yeah, I don't think this is. And it's but what it says instead is this defines a type, and so it's saying given x, give me a value of this type, and that's why down here the Copilot or whatever tried to generate a like an implementation where it gave the number 2. So this just does not work. What's wrong with this though? Failed to synthesize diagnostic. I'm not sure that the diagnostic information is all that helpful. What is wrong here? Okay. Didn't really give me any more diagnostics. Oh, it did. Ambiguous possible interpretations, prime sieve state next step. Yeah, I don't know if I can do this either. So let me just stick to. I'm doing a lot of experimenting rather than just doing what I know how to do, right? I'm trying to learn, but over the map here. All right. Maybe we'll try. That's it. It's supposed to be turned it off. Okay. What do you replace it with an underscore? Yeah. Hmm. So I guess anything can implement the state. But if I wanted to say if I implement the spec, that's obviously not going to work because I can't do that without actually proving things. State doesn't have any proofs attached to it. All right. Anyway, so he rates this like this. But I don't think this makes sense because this would, he over optimized here. Like what? Because it's not that I want to prove these things. Like I'm taking apart and I'm like leaving some structure here that is like redundant in a mathematical sense. I'm trying to like give you something to attach, like a structure you can attach to, even though it's like right here everything's optimized away except there's some prime, and then you're talking about the sets that are the sets that a prime sieve would track. But then he showed me how to do a He optimized away this prime sieve state thing. I don't. What I'm seeing here, right? I mean, I created these fields. He like isolated them and put them into this this structure form. Or he broke this into two things and with some definitions. I've lost track. I've lost something. Oh yeah, so we need these are my these are the states. So if you want your spec, okay, so you need let's write what I have to actually prove. So you have let's leave these. I'm not sure what I did earlier about extracting this to a thing makes any sense. Let's leave this here. Put these arguments back. So at every step, we'll take an instance of the state. So X is the state. And then from that, we're going to give a proof of all these. We have a hypothesis. And these are the things we have to prove. All right, so if it is a prime, we already know that, let's get rid of this instance. Maybe we'll put that down later. We know that C is prime. I'm going to put this at like stuff. Maybe I'll put this in scratch. Garbage. These are already checked into version control. Not really. Everything below this line is like scratch right now. Maybe I can salvage something. All right, so the prime sieve has these two variables, C and C prime. Which is this. So C prime is this. So the mere fact that you implement this, you have to provide a proof that C is prime. And then other than that, you just have to provide the init and next method. So init would be your initial state. And then once you get this, then once you try to implement this, you have to prove that the initial state follows all these things and next implement. You have to do a proof by cases, I would think. So every one of these is going to be a proof that looks a little bit like an induction proof, where you prove it for the initial case. And then in the next case, you have this coming in. So because you're given a value that is, that I guess it satisfies prime sieve spec, then you have all these hypotheses are granted for you. So the input is already correct, and then now you just have to prove that the output is correct. So then you have to, this is your base case, and this is the induction step. It's not really induction, but it's very similar to induction. I don't know what else to call it. And so every one of these proofs would be of that form. I think. So maybe let's make one. Structure. Dumb prime. So C is the current prime. You don't need any of these things. And then we say instance state dumb prime gen, where C is just the prime that we're looking at. We're going to initialize C to be 2. And then next is going to be, has to take a prime gen. So it's going to be lam. And take an x. We're going to say x.c. Oh, so that is a prime. But what I want to do is just look at every number up until then. So I think like that looks reasonable, but it's saying like nat prime. You can't just generate every number of that set, can you? I think you say nat find so let's look at what that is. Print nat.find. Why is nothing happening? This should give me an error, but this should be fine. So let me. Oh, maybe it's trying to find out. Maybe it is doing that. It's looping through all the integers. I don't know. Let's just change this to sorry right now. All right. So nat find is if it's decidable, then we're going to find an instance of this. So given x, nat find and then take that. We're going to say so given some number n, nat.prime n. How about the simpler thing, n is greater than x dot c and nat prime n. Well, what's wrong with that? Nat prime argument n has type n prime pivot expected to have type. Wait, what? Oh, it's like it has subclassed the whole thing. So this is an n prime. Interesting. All right, so we don't need this. We just find p val is greater than x dot c dot val, right? Why is that like it? What is the argument to nat prime? Oh, maybe because I have the word sorry after it. So I don't know if this is actually going to execute it. So is there a proof that exists? Yeah. Uh, but I have to provide it. I have to provide a proof that this number exists. Right? I have to provide this hypothesis. So if P is a decidable predicate on N, and is nat dot prime decidable? I don't know how to tell. Print nat dot prime. I guess it'll tell me, right? If I do this, it'll tell me. Right, so I have to prove. Right, so let's call this next prime. Say def next prime, or we'll say let's call it next, right? But sorry didn't work. I think these are in the wrong place. I think this needs to be here, and this needs to be here. Okay, that still didn't work. This needs to be a type proposition. Okay. No, we don't need this x, right? So next is given a Back later. I don't know how to use NetFind. All right, so show me how to use NetFind. How about this? Copilot. Show me how to use NetFind. I have found that these LLMs are, they say they hallucinate quite a bit. For the less mainstream your language is, the more obscure. Like, see, like this is not a keyword in Lean. This is, I think, from Lean 3. And this model is not. Yeah, this is garbage. So this is I've gotten better results from just talking directly to Claude or I mean, you can ask on the channel, but so we'll say show me how to use nat.find in sieve. So the argument to not find here is x. So first of all, let's see if this works. See if this is a hallucination or not. That should always be the first step. Just test it to see if it's garbage or not. So if this, yeah, that's actually not a problem. Oh, it's called. I don't even think you need this. I think that used to exist and it no longer does. A lot of we don't need mathlib for this at all. This should work. Why isn't it? Import data nat, which is the no. Oh, it's lean.datanet, right? Lean.data. Right. The control space should be Copilot is stealing it. Yeah, turn off Copilot. Or give it a different name. Because then you can just use the IntelliSense. I thought it was data. Huh? Okay, so how about this? We say find. No, but nothing's working here, right? Find nat.find, right? I could have sworn that was the thing. Okay. Well, I'm just stupid now. Nothing, huh? import. Not that. That's Mathlib 3 DataNet Basic, right? Init DataNet. Now I should look for nat.find. Mathlib init should be looking in here, so I should look for nat.find in here, which it looks like is in this file. There we go. That's what I wanted. Okay. Now where do I see how do I close it? Okay. It's not going to go away. Question is, how do I get it? So I get mathlib init data. Maybe I say import mathlib. Oh, I'm blocking this. I don't know how to see what it's doing when it just freezes up like this. No output. I don't know if Lean is crashed. Restart the server. Busily processing. Okay, at least it's showing me something now. Maybe I'm importing just way too much stuff because okay, so init. Somehow if I do this, it's gonna. I gotta go get my daughter some milk, so second here, and I will be back in just a hopefully that'll update. Okay, back. So, I kind of wanted to document my learning curve on this. So, it's not meant to be a tutorial. I'm recording what I'm doing so that I make my good video. Maybe I can use some of this footage to show how annoying it was to learn this stuff. All right, so fine, still not. Okay, this is actually good. Right, because now I've got an error here. Oh, something just popped up saying just might have. Yeah, so this universally happens with ChatGPT things, but sometimes they give you like useful. So at least it'll explain things, and sometimes that's a hallucination too. But it's usually by going through a few iterations of this. Um, I don't believe. Yeah, and it's talking about basic, which does not exist. So that's so let's look for this. Part of the problem is it's out of date, right? Okay, so wait. Yeah. And then you say like nat dot. Okay, so that is there. What? Oh, decidable. See, like that worked, but I had to go from decidable LT to deck LT, and it's just things that get renamed or whatever, and you have to go on like a little hunt, but it pointed me in the right direction. So I don't think we're in any danger of these things becoming mathematicians anytime soon. But to be fair, they're not. They're, I'm pretty sure that the math lib has been changing dramatically since the cutoff date on these. Claude is not much better. Okay, so all of this was to figure out how to use nat.find. So and I did see in there something else. So let's see. Let's find nat prime. Hey, sweetie. You need water? What do you need? Oh, your tooth fell out. You put all your teeth back in, okay? We'll save that. put it into the box. Okay? Does it hurt? Just fell right out. All right. I hope you keep some in your head for a little while, okay? A 6-year-old losing some teeth. All right. What was I gonna do? And I'm gonna say my predicate is gonna have to take 2 arguments now. Well, let's just prove this one first. We know that this is true. I saw nat decidable prime. N. So hopefully this would not work, right? Like this would fail, right? From a type error. Right. So if I now that I can show that that's prime, well, I'm gonna paste this into the actual code. This is the function I want to do. I want to say nat prime. So we have, and so we'll say p is prime, nat prime p, and p is greater than c. P is greater than c. Okay. So then now we have to say we have to prove this somehow. And I think we need. I'm going to try and prove this. So this is what we call a tactical a term proof. Right? So I think, and I haven't done this really much. I haven't done it this way. So normally you write the word by here and then you use some tactics, but the tactics are generating a term proof. So what do I need here? If I put an underscore here, it's supposed to tell me type n. Okay. So I need to say given c. So first of all, let's swap these. Right, because we need 2 things here. So now, right? How about this? There we go. Not be used where a function is. So if I say by here, it'll tell me what the goal is. If I say sorry here, it'll tell me what the goal is. I need to show that it's a decidable pred. So I don't know how to deconstruct that. How do you deconstruct something? No, I don't need this. I need a function. This is not a proof. Okay, I'm done. Done here. So we need to show this. So we need to give it a key. So we say now we have a proof, right? So I'm just like losing here. Anything but equals. We need equals. This is the instance. non-identifier n. I call it p. That's fine. Term has type I had just seen a function about it. I mean, talk about question about it. Right there in the new members chat. How to make a decidable instance. Let's try this. We say, for instance, as decidable application type mismatch. En argument n has type expected to have type n of types. I need a oh, I see. So it didn't just pass in the right thing. I need to pass in what? I need to pass in a value. Maybe I just put this in there? How do I get to n? Where does n come from? Say lambda n here. So that is a decidable function argument type n prop type, but is expected to have prop type. Doesn't know what that is. Can I just fill that in with anything? I have no idea how to do this. But what does it say? Okay, it's telling me use set up. Okay, it's telling me fail to synthesize decidable PCMs. It just made up a term here. Let's see. Look at the. He made a good point. Look at the definition of and for instance as the definition. Mm-hmm. Well, okay. How about this? Have decidable at prime I don't need a proof here. No. No. I don't know if I'm even on the right track. So say dp and then d less than is what am I doing? Decidable pred p greater than c. That equals nat dec lt, right? And then from I need something that says like that like the and of two things is decidable. Let's show decidable pred I think I need like a fake P over here somewhere. Refer to the argument. I don't know. Maybe I don't need like it synthesized. Decidable pred P is the goal, right? So I don't really need this. So we can say simp P no rewrite P. Oh, okay. So hang on a second. This didn't work. This doesn't look like it. It's working right. Like this needs to refer to P, right? P. I'm just completely screwing this up. This is not like a proof. I don't know how to show that this is an instance of decidable. I'm completely lost here. I'm just making stuff up. That, like, I'm not getting any feedback now. There's no error message, anything like that. Maybe I just need to have it return a Boolean. I don't know what decidable is. How do I know what decidable is? How do I do? Like, I mean, I get the basic idea. I've got to show. I probably maybe I don't get the basic idea. Decidable. How do I show that the and of two decidable propositions is decidable? Hmm. Okay, so this is a predicate that takes a piece. I don't. I'm wondering if I feel so dumb right now. Not dumb. I don't feel dumb. I feel like I'm gonna figure this out eventually. I'm lost here. Like I don't know what I'm doing yet. I'm just kind of fumbling around. Okay, so instance decidable, but it doesn't have to be a decidable predicate. It just needs to be right. Decidable. There we go. That is a more useful idea. How do I say CP? Okay, decidable CP. So I'm going to say that P is the prime is decidable. Okay, decidable prime, and H decidable less than. How about just decidable? What is this? I can write this as C less than P, right? So we can just fix that. I'm sure there's like all kinds of, okay, so that still didn't help me. Okay. So we need to say C add up here, and maybe. How's that? Better? And we say CP. So those two things are decidable, and now I need to show this is decidable, and I rewrite, I can't. I can say by up here. Now I can use rewrite P. Now it says decidable nat prime. I can say intro how about I rewrite this and I rewrite less than or rewrite left HDP HDP. No, I need to say intro, apply and intro. But I need more like a apply. Oh, can I do that? That work? I did nothing. There needs to be like a decidable. There decidable and. E. By inst decidable and. Okay, that did something. Like somehow I need, so this is telling me what I need to prove. And I have that these two things are provable. So the two sides of the and are both provable. Can I even say this, nat prime P? Yeah, that worked. I think. Maybe it didn't work. I can't. This is the predicate. I have no idea what I'm doing. Is there an intro? Is Wait, did I prove it? I need this. It proved it. Okay. So, like, I don't know what I did. I don't know what I did, but that proved it. Okay. So now, theorem exists n such that p. All right. So now I want to say that for all c, there exists an n such that c and how about we call it? For all c there exists a, so for all the cutoffs or whatever, and the proof is so I have to prove that there's a next prime, and that there should be something like so. For all cn, right, so we can say not obtain, we say intro n, we introduce an n, or introduce a c, right? It doesn't matter what you call it, but we're introducing a value here, and then we're going to intro a p, intros, intro c, intro p. Oh no, we have to say use p. I would say obtain p. So we have to simp on the definition of the predicate. Okay, so then now we say there exists a p such that nat prime p and c is greater than p, and then how do I do this? I need to I need to create a value of this type. So I need to say obtain how do I know that this exists? We say nat prime in all of this is just like I wonder if this thing has a prime generator, like something that generates a prime. Because all I wanted to do was just say, that there is a next prime. I know there's a next prime. It exists. Exists infinite primes. All right, so this is it. This is maybe I can even just put this in here. I can say exact because it's not exact. I need. How do I use this? I need to say. So how do I? Let's print this. Print not exist. What I just saw over here. So given an n, I get this. I get back a type that says p is n, and it's not exactly right because it has some equal sign. So I'm still like I'm treating this like it works by magic and it doesn't. Like, so I'm not thinking clearly about what this is. So I have a term here. But this put me in tactic mode. So how do I use a term when I'm in tactic mode? So I can say exactly this, I think. I can say have exist prime, and the proof of that is exist. I don't even have to use a tactic here. I can just say n. Maybe c, and I pass in c, right? Because I'm taking this term here. This function takes this theorem takes two arguments. It takes a natural number and it returns this, or sorry, it takes one argument. It takes this argument and returns this. If you think of it as a function, right? So if I pass in c, then n is replaced with c, and I get this statement. There we go. Okay. And then from that statement, now I have this as a fact in my, and I say, I think I can say let P, like I think I can destructure this. P HCP, oops, sorry, HCP and H prime of this. Yeah, so I can destructure that statement by using these little angle brackets. You type backslash and then bracket, and that's a destructuring kind of thing. All right, so now I have those. I'm expecting to see three names over here. Maybe I say have. Sorry, have. Still no three names. Not done? No. Say obtain. Say have this. I just don't know the syntax of how to do this. It equals this. Is that right? Yes, and now we have these three variables. Am I fooling myself? And we did not have them before. Oh, did I just not see these? They're right in front of my face. DNP and HCP. Okay. Yeah, I think I don't know. I think I was confusing myself, and I just did not see these things. My mind is elsewhere. Okay. So yeah, this destructures that. And so now I actually have those things. I've got two variables, C and P, less than P. But I actually need it to be, might have an off by one error here. Because I want to say there is a next prime. That we can find the next prime. What is it? The smallest prime greater than 2. Are you kidding me? Instead of for all, let's just make this C nat. This C nat, and then we're going to say, so we don't need to introduce C. Boom, boom. Still proven by sorry, but just assuming we, like it doesn't make sense to prove something if it doesn't get you to the answer. we pass in the 2 here, and then we find the smallest next prime of C at the X next prime, and we say X next prime. So that works. And now let's see. So eval next prime of 2, 3, 5, 7. Okay. You put in a number, it finds the next prime. Okay. So this is what I was working for. This was the dumb sieve I wanted to, or the dumb prime generator I wanted to make. So even though I had like I want him to be able to show. I think I started this like 10 years ago now. How many? I've been at this for 2 hours and 51 minutes. So like somewhere like an hour and a half ago, I decided that I would just make a one-liner thing that would find the next prime. This is the next prime, right? You know that it exists because you have a natural number. Find the next prime greater than that. So you pass it eval next prime 2, 3. If I give it 0, it should give me 2. Okay, this is good. So this is a prime sieve. That's actually fascinating. This will go into the video. That if you can prove something exists, Lean will find it for you. And you don't know how it works. Like who knows? Presumably, it's just generating every single number and testing it. And so, yeah. Presumably, this is like looping through all the potential factors up to a power of up to the square root or something. I suppose you got a list of primes. I don't know. How about not decidable prime? I wonder what that is. Oh, so let's finish this proof. I do want to see what that is. Find min fact. Find decidable prime net. I don't know what this little triangle is. Macro. H A equals B and E. Yeah, the term HE has type PB. HE is like a substitution. Here, E is saying min fac equals P, minimum factor is equal to P, and use that to rewrite the expression. Okay, curious. Good to know. All right, so anyway, now, can I use that here? Do I need this? No, so I don't even need these. I need this. Yes, I need that. How that works. Okay. But I should say like C+1 here. I should say I want to introduce a variable. Let d equals C+1. And we'll say d here, and we'll say d here. Well, that actually just worked. D. They use p. And so I have this statement, and I want to eliminate this thing, so I use p. I have a thing now called p that is prime, and I can see that it is prime. P, and then I can say and intro. And intro. Now I have two cases. How about say cases? And we say case left. Now say case left. It doesn't matter. You can indent it. There's a way to like structure these. So we have this factor. We have to prove nat prime p, and so we have exact h prime. Yes. No, you don't indent. Okay. Indenting means something. I don't know what. And then in c less than p, we say by rel. I say have c less than p. Maybe. So now we have to do that, and then show c less than p by rel. Rel not a thing. So using with okay, I don't know. Rel. By rel. Have c less than p equals by rel. By linearith will do this. You have to import linearith. Import mathlib tactics linearith. Linearith. The tactic. And now this works. I have to restart. Is it doing something? I easily process. Take its time, and then it should be trivial. The word should be trivial. Exactly this. That's the proof. I think you can say show. Show sieve. What is the syntax of show? I don't. The word show is so hard to search for. How do you find the syntax? There's no quick reference. It's like every time I want to do anything, look all over for demonstrate. Where did I find this? Kind of like don't want to. I want to look at called proving theorems in MathLib. Lean github.org. GitHub.io. Prover. That's going to take me to what? Lean Lang. Okay, so documentation. Theorem proving in Lean 4 is the book I'm looking for. In here we say I think the word show is documented. Show P from HB. Okay, that's what. Show P from. So I guess you could say show from. There is no statement that says HCP, right? You need to have a hypothesis. I don't know what the syntax of show is. I don't know how to get to a reference for this keyword. I don't. MathLib documentation. Open. You need to open something? Bring it here, sweetie. There is documentation for this thing, but it is not well organized. Like these, you'll go to these books, and the books are empty. Whole chapters are just the word to do, which I'm not complaining. I mean, I guess I'm complaining. Come here, sweetie. Oh, hello. Here you go. I'm gonna come down a little bit. I'm wasting time on this. sit with them down. I really just kind of wanted to document my learning curve here. At some point, all this stuff is going to be in my head. Maybe I'll write like the manual. Like everything's a work in progress. I should like bookmark. It's quick start, but not quick start for like proving things. I've forgotten what I'm looking for now. Anyway, I wanted to know how to do this show command. I don't. There's just not a reference, right? You have to dig through here and like you have general topics on how to do things, but there's not yet a quick reference. The mechanics of proof actually has an index of lean tactics. I have that open in another tab right here. I'm using that as but it doesn't have like a quick reference anywhere. This is the closest thing I found to a quick. So I think I need something to refer to. Like there's no lean for quick reference. Yeah. Yeah, it's just that you need to organize your documentation in a way that is all in that gives you different views. So there's like a lot of tutorial stuff, but there's not yet a lot of like quick reference, as far as I can tell. And I agree, we need both. And this is somebody's got to do the work to put this in. So can't blame him for that. Anyway, so that's why I've been using a lot of like Chat GPT and stuff, just to tell me what to look for, because it have a reference, and maybe it would be good to put things together like that. Okay, so I no longer have the proof. Right, so the end, so the base left. Did you say match? Yeah, and intro, and then you do with left. Again, a quick reference would help me out so much here. Like I've seen this like in 20 different places, but now that it's time to actually use it, I don't know. So like X left, doesn't matter. Let's not use this stuff that we don't know how to use. Say exact H prime. Okay, apply and intro exact H prime. I think you can say this. Gives it a little. Get what the dot stands for. And then that way you can have like a bulleted list. And so I need to prove this, and so I can do that again by literate. Literate. And then that solves the problem. Okay. And I don't think we need to give this a name. Just because of because the line below has, and we need, oops. Okay. All right, so that's a proof. And then now we have a prime, not a prime sieve, but a brute force prime finder. So call this Is next prime is prime. I will say prime greater than prime GT. Prime GT, and we say our predicate is prime GT. GT, and then let's see if we can say C. Do we even need this? Prime greater than, and then simp again prime. I should have done that. All right, so there we go. So we have and we'll call this prime greater than. So not find. I think you can use a $sign here too. I don't know what the difference is. When I do this, I can hover my mouse over this, and it was able to show me Haskell-like pipe operator. When I use a $sign here, oh, alternate syntax for this. All right, so they mean exactly the same. And this means something too. Pipe operator. I kind of am used to the $sign. But we could do it like that too. Okay. So this is so here I have a prime sieve. Okay, and let me copy this and put this in prime, and we'll check this. Or Like what I wanted to do was okay. What I wanted to do was make this one-liner here that would find the next prime, but I had to do all this work to make it happen. And in doing that, like, what did I do? I proved that there is a prime greater than C. That for some natural number, there's a prime greater than that natural number, which is a statement of the. This is something that probably, if I were able to search better, maybe I would be able to find this thing. So again, there's a word called section, and I don't know how to use that word. How do I use? Organizational features, variables and sections. Not even simple gen. Simple. Call it dumb gen. And simple gen. So the point was that I wanted to be able to use this framework to. Yeah. I should check this code in. Right? Put all this inside of here. Dumb. Say simple gen. And then in the instance of this, hmm, oh, init is going to be C is going to be 2 by nat prime 2, and then next is going to be next x. So init next x is going to be can we make it n prime? So we have to prove this instance citable n prime. No. I think you. I think you just say. Let's leave this alone. This is a nat. F next n prime c nat n prime. So how do you do this typecast? You can't do it unless you have a proof. And so you can say it's just like this. You have to provide a this, and you're going to say next prime of c. Now we have to prove that that's we have to prove that it's actually an n prime, which means that it's prime, right? So I sorry. What is the proof? X prime. I don't know how you break into this, but How do I complete the proof? Say complete this proof. I don't think it's going to work. Oh, a fine spec. Interesting. Okay. Apply at spec. Again, could be complete hallucination. X prime greater than BC property exists. What if instead of that we said n prime find? You inherit something like that? No, n prime find does not exist. Say nat let r, the result, equals this. And r, and I have to show that it's prime by that'll work. You ought to be able to prove this. Like, it's the condition. But it kind of like discards it. You don't get back a proof. You don't have a. You're just getting back a nat. You're not getting. There's nothing attached to it. It says that it actually doesn't remember what the predicate was. That's not going to work. Isabel had as a thing called sledgehammer. Try and guess things. I guess Lean's tactics could do that, but that's already what I asked, right? This didn't. You'd think there'd be one that would have this thing, right? Nah. Yeah. in LeanSieve, I can just give it code. I didn't know how to. Oh, it copied the formatting from. Next prime. Success regenerates primes. But how can I force it to include proof that generates x prime greater than c, that the result is prime. Proof term stating, how can I change this to also include modify the function to return the next and proof of its primality. It means could done using a dependent character. Yes. That. That. Right. When I give things to Claude, though, when I give these responses, it's actually pretty good at correcting itself. Type to fix this, we need to use subtype instead of. If I feed these in, it's probably going to come up with the answer. I just ignore everything it says. I try the code, I tell it what the error is. Sometimes it churns and it just can't find it. The proof of the predicate, not a subtype. Okay. There we go. Okay. So I don't have any idea what this does, but like Claude got there. But this is a proof of and if I want it to be an n prime, I need to say, okay, so def prime greater than is a type, and it's going to equal this. So I declare that type. Nat, and then I can say prime d in lowercase prime gt c. Then from here, once I have this, I think this is clunky. This seems like it. I might ask about this. Seems like this would do the search twice. But now, we could call this a def or a theorem or whatever, but theorem n prime of prime gt. We just need to convert between. And that is that if I have a prime p of c of anything, then I can get back say like if p is a prime gt, then we should be able to say n prime. Maybe just n prime. I don't even know. You know what? I'm just gonna stop this. People keep ringing my phone, so I'm gonna end this and do a little later when I have some. I captured the idea that this is humbling. So thanks for watching.